So today's URM lunch is happening in again in the hotel restaurant AJ's Tavern just over there, and we have a big tent picture of what URM means. So even if you didn't sign up at registration, feel free to join. Okay, and again, these are led by our inclusion chairs, Willow and Christine. And then our last sort of get-together, last hike in Chautauqua meetup is this afternoon. So if you missed the ones on Monday or Tuesday, this is your opportunity to get in on this. And Dakota, our social chair, will be leading the Chautauqua hike. Again, meet up right outside in the foyer. Okay. So with that, I think we should turn our attention to our last keynote session. And I'll get Alice up here to set up. Okay. All right. So I am so thrilled to be here to be introducing our PLDI keynote speaker today, Professor Alice Alberguthi. Alice is an associate professor of computer science at the University of Wisconsin-Madison. After having received his PhD from the University of Toronto in 2015, Alice has an incredible track record of doing deep and thoughtful work. He is well known for his work in program verification with interpolance and program synthesis in a wide variety of contexts. He has won several distinguished paper awards, including a SIGPlan highlight for his PLDI 2020 paper. Alice has had research awards from all the major companies, Google, Facebook, Amazon, as well as an NSF Career Award. He has also written a monograph on an introduction to neural network verification that is, I find, one of the most approachable resources on the topic. And now, for the past few years, he has turned his attention to the software stack for future quantum computers, which I am eager to learn much more about today. So we're really honored to have him here today. So thank you, Alice.
I'm very honored to be here, so thank you for the introduction, thank you for the invitation, and thank you all for coming. So we'll begin our story at the beginning. The year is 1900, the month is October, and the city is Berlin. And the man in question is Max Planck. That's right. He invented the Planck. So Max was working on a problem and he was stuck. He couldn't solve it. And the PLDI deadline was approaching. After all, it was October, right? PL back then stood for physical laws and not programming languages. There were no programming languages back then. So the problem looked like this. It was the amount of radiation emitted from an object when you heat it up. And the empirical data looked like this, these curves for different temperatures. You don't have to understand what it means. And the theory predicted the following. So it was completely off, a very different prediction. And Max wanted to fit the theory to the data. And in his words, this is real, in an act of desperation, he decided, you know what? I'm going to assume that energy is not a continuous quantity. Energy, it comes in discrete little packets, just like the weight plates on his back. And this was the invention of course, Planck's constant. So he submitted the paper to PLDI. It got accepted. Of course, reviewer number 2 complained as usual. They said, how is this science? This is just curve fitting. But it got accepted. And finally, this became the birth of quantum mechanics in 1900. Now, it took people like 3 or 4 decades to fully flesh out the theory of quantum mechanics and come to grips with the fact that nature is indeed stochastic, that a particle can be here and there, that the cat is both dead and alive, and that God does indeed play dice with the universe. And of course, this created a lot of philosophical implications about free will, about the many worlds hypothesis, and on and on and on. But this is a PL conference. We don't care about philosophy. We care about semantics, right? So how do quantum computers work? Interestingly, it took people another half century to even just think about quantum computing. And we had to wait until the early 80s. And like many things in the early 80s, it arose as an idea both in the Soviet Union and the United States. So first in the Soviet Union in 1980 by Yuri Manin, and then a year later here in the United States by Richard Feynman. And both of them recognized that quantum mechanics is complex. Okay? If you have a system with n degrees of freedom, like n electrons, just to write down its state requires an exponential in n. Okay? So we recognize there's an exponential explosion. Manin was a mathematician, so he recognized that this is potentially a powerful computational model because you can fit more in a state. Feynman was a physicist, so he was interested in simulating physics on a computer, and he couldn't do it on a classical computer. So he's like, let's fight fire with fire. Let's build a quantum computer to simulate quantum mechanics. And then it took about a decade of progress to fully flesh out the idea of quantum computing, and then the bangers started dropping in the mid-90s. So the first event was Shor's algorithm in 1994, who showed that you can actually factor integers in polynomial time on a quantum computer, something that we don't know how to do in polynomial time on a classical computer, and it underpins a lot of cryptography. So if a powerful quantum computer arrives today and you get your hands on it, you'll be able to steal all the Bitcoin and become a trillionaire. Of course, if you do it in one shot, the value will plummet to 0. So you have to be pretty careful, like do it one iced latte at a time, and no one will catch you. So a couple years later, Lloyd demonstrated that you can actually indeed simulate quantum mechanics on a quantum computer efficiently. And this gave people a lot of ideas about simulating quantum mechanics for drug design, for material discovery, and so on. And these have animated quantum computing research since then for the past 3 decades. Okay? And some people argue that coming up with building quantum computers will usher in a new industrial revolution. So before we begin, I'm going to give you a crash course in quantum computing. A lot of people tell me quantum computing is scary. I'm going to show you that it's not actually scary at all. So this is a normal bit. It can be 0 or 1, and you can flip-flop between 0 and 1. And if you do it really, really fast, then miraculously you have a computer. Quantum bit is the same. It can be 0 and 1, and you can flip between 0 and 1. But you can also be in a little bit of 0 and a little bit of 1. This is known as superposition. A particle can be here and there. The cat can be dead and alive. So the little bit of 0 and a little bit of 1 is called the amplitude. It's usually a complex number. And the 0 and 1, we typically call them basis states. Now, if you had more than 1 bit, okay, then you have 2 to the n amplitudes. And this is why Feynman and Manin were very excited about quantum computing. So quantum operations, you can operate on a quantum state. You can think of them as maps in the functional programming sense, where you look at every pair of basis state and amplitude, and you're transforming it into a new basis state and amplitude. Okay? So for example, the negation operation, or flipping a bit on a quantum computer, looks like this. The 0 becomes a 1, and the 1 becomes a 0. So effectively, they swap their amplitudes. Okay? And typically, people write quantum programs as circuits, so you'll see things like this in a textbook. So this is the negation operation, an X. And you read it from left to right. So the state comes in, its amplitudes get swapped, and comes out on the right. This is a Hadamard operation. You take an amplitude and you split it in half. So you get something like this. Right? The amplitude of 1 also gets split in half, but the amplitude of 1 is 0, and 0 divided by 2 is still 0, so nothing really happens. In a circuit, you see it like this as well. It's just the letter H. Now, you can do interesting things in quantum computers where you can actually multiply the amplitude by a number. So here I'm going to multiply the first amplitude by 1 and the second amplitude by -1. Okay? So you can have negative amplitudes. Generally speaking, you can multiply an amplitude by any complex number on the unit circle. Here I just chose 1 and minus 1 for simplicity so we can visualize it. And in fact, the power of quantum computing comes from the fact that you can multiply by any complex numbers, and you can generate things called the magic states using those. Okay? And typically you define this complex number by the angle along the circle. All right. Finally, we need binary operations. The standard binary operation on a quantum computer is the C0. Think of it as an if statement. If the first bit is 1, then you flip the second bit. So in this example over here, for the first two basis state, the first bit is 0, so the if statement does not kick in. And on the two other amplitudes on the right, the first bit is 1, so the second bit flips, and therefore the amplitudes get swapped. And this is what causes entanglement in quantum mechanics. And typically you see it in a circuit looking like this, where the first bit is the wire on top, and the second bit is the wire on the bottom. This plus sign is really an XOR, because you're really doing an XOR operation over here. Finally, measurement. Ideally, you should be able to ask, give me the amplitude of 0 or give me the amplitude of 1, just like you would read the contents of a memory address. Okay? But quantum mechanics does not let you do that. It lets you measure the state. So specifically, you look at the state like this, and you treat these amplitudes as if they are probabilities. If the amplitudes are negative, you just treat them as positive. Okay? So this is a probability distribution now, as far as we're concerned. And you're sampling from this uniform probability distribution. So if you measure this state, you're going to get 0 with probability half, 1 with probability half. Okay. So suppose, for the sake of illustration, that we measure and we get 0. Okay. Now, what happens next is that we condition on the observed value. So it's just a conditioning operation. So 0 remains intact, and the amplitude of 1 disappears. Okay. Standard conditioning operations, but physicists have a flair for the dramatic. So they say the state has collapsed. Okay? You can, of course, normalize the state such that everything sums up to 1, but it's not shown here because I'm not very good at Keynote. Okay. So this is measurement. Finally, you can put things together into circuits, everything that I showed you. This is a circuit with 3 operations. You perform an X on the first qubit, a Hadamard on the second qubit, and then there's this if statement between the 2 qubits. And you can write it down in assembly-like language like this as one instruction at a time. So these 4 or 5 slides are everything you need to know about quantum computing. If you locked yourself up in a room with these slides, no access to the internet, sufficient amounts of food, and patience, you'll be able to derive everything that we know today about quantum computing, more or less. Maybe you need a couple more facts, but that's it. Right. So because of the profound implications of quantum computing, people have been building quantum computers. And typically in the press, quantum computers look like this, like these chandeliers. This is not a computer. This is a fridge. It's a very expensive fridge and a very good one. It takes temperature down to very close to absolute 0. And it's needed for certain kinds of quantum computers, typically built using superconducting qubits and superconducting circuits, which was the topic of this year's Nobel Prize winners in physics. This is another kind of quantum computer called a neutral atom quantum computer. It looks very different. Things are very cold, but they're very locally cold, and they're cooled using lasers. And there are many other kinds of quantum computers, photonic quantum computers and spin qubit computers and trapped ion computers. There's a Cambrian explosion in the kinds of hardware that people are trying to build to be the first to discover the quantum transistor. Now, when we think of the power of a quantum computer, typically the best number to describe it is how many qubits does it have. Okay. And right now, we're roughly over here. We're building computers with on the order of hundreds of qubits that we can store and manipulate. But the interesting applications are roughly in the millions or hundreds of thousands of qubits, whether you want to break encryption or you want to simulate chemistry. So this looks like an insurmountable gap. It's gigantic, right? But what's interesting is that this gap is shrinking from both directions. Physicists and engineers are building more and more qubits and more reliable qubits. So the gap is shifting from the left. And people are figuring out how to design better computers using computer architecture, how to design better error-correcting codes, and more efficient ones, and how to design better algorithms. So we're seeing a shift from the right as well. A key example here is a paper from a few months ago that made a big buzz, where they argued that you can actually implement Shor's algorithm on cryptographically relevant problems using only 10,000 qubits, if you can build such a computer. Okay, so there's a lot of excitement in this convergence. And I'm going to argue that actually PL research can help this convergence arrive faster. Right. This brings me to today's topic, the rise and collapse of a quantum state. So a quantum state is conceived as an idea in the mind of a scientist. I want to construct a state, and I want to measure it. It's initially an abstraction, a specification, if you will. Okay. Then this specification is born and becomes a computational artifact. And this computational artifact is typically a circuit. And then this circuit undergoes a sequence of metamorphoses. It gets decomposed, it gets optimized, it gets lean, and finally it's ready to enter the dark and bitter cold confines of a quantum computer and meet its final collapse. So we're going to walk through the story one chapter at a time, and I'm going to use work from my own group to illustrate how PL research can help in each of these chapters, as well as work from other folks in the community. Okay. And I'm going to describe a set of open problems that I think can allow the PL community to help accelerate the progress towards viable quantum computing. And I think the PL community can help in 3 different ways. One is abstraction. We're really good at lifting the level of abstraction and eliminating manual and tedious and repetitive and error-prone work, whether it's using PL design, program synthesis, strong compilers, etc. The second is optimization. We've been building optimizing compilers for decades. And I always tell students that if you remove optimizing compilers from the world, civilizations collapse. Yeah. So in the quantum computing space, optimization is even more important because these computers are resource constrained, they're error prone, so your computation has to be as optimal as possible before it hits the physics and the lasers. And finally, verification. A quantum state takes a very long trip before it gets to a quantum device. And every step of the way, if you make a mistake, it's completely disastrous because ultimately we're using computers, quantum computers, to do things that we do not understand. So we don't even know what the right answer is or what it even looks like. Okay? So any mistake along the way is problematic, and we want to prove that everything we're doing is actually correct. So let's start at the beginning. Imagine a quantum chemist who wants to simulate some chemical, perhaps a chemical that looks like this. Maybe they're designing a new drug, and they want to understand what it's like if you ingest this drug, wait 10 more minutes. To do that, what they do is they build a model. Power. Power is back. You get it back. It's like this. What's that?
It's there and up there.
Superposition? All right. Hello, hello. Can you hear me in the back? Should I keep going?
More power.
More power. Sweet. Can you hear me? No? Yes? Yes? Well, clearly you're hearing me because you're shaking your heads. Hello, hello? Hello? Is good in the back? All right, so they build a model of the chemical, right? Remember there was a chemical or when it was simulated? Okay, here's the model. It looks like this. You don't have to understand what it means, but it has the letter T. T is time. Okay, so you can ask, what's it going to look like in 10 minutes or something like that. What's interesting is that this model is relatively easy to write down on a piece of paper by a chemist, but it's really hard to translate into something that you can execute, hard to translate into a circuit. Okay? So this is what Seth Lloyd discovered back in 1996 when in his answer to Feynman, is that you can actually do that, and you do that using a number of steps. First, you approximate this model. Okay? You don't have to understand what this means, but essentially you slice space and time into little small models. And you can translate then each of these models into a circuit really easily using a process called circuit synthesis. And then you can stitch all these circuits together and execute them on a quantum computer. Now, this looks nice and clean and beautiful, but in practice, when you talk to folks in quantum chemistry, in energy fusion, in computational physics, they're using a hodgepodge of tools to decide which approximations to use, how do you turn things into a circuit. They're really working at the level of assembly language. Okay? And to be honest, quantum chemists should not be working at the level of assembly language. They should be working at the level of models, modeling chemistry. Okay? So as a PL community, we have an opportunity to build compilers that take things all the way from high-level models down to optimized circuits. Okay? And it's a very challenging problem. Additionally, these compilers ideally are verified to be correct. And here the verification condition is different than what we're used to, where the source program is equal to the target program. Instead, the verification condition is approximate. Because we're doing approximation along the way, it's not an exact equality. Okay? So it's a challenging problem, but we're seeing interesting new insights. Just this PLDI 2 days ago, my colleague Charles Yuan presented this distinguished paper on abstractions for quantum linear algebra, which can encompass some of these quantum simulation problems and techniques. And if we step back from quantum simulation and natural science and think about algorithms in general, typically when we think of quantum algorithms, we think of high-level specifications that look like that. This scary-looking expression is the quantum Fourier transform. You don't have to understand what it means, but it's very common. And this gets translated into circuits with thousands of operations. Okay? So clearly, the path from going from a high-level mathematical specification that an algorithm designer thinks of to a circuit is incredibly long. It's actually a synthesis problem, and in the worst case, it devolves into enumeration. Okay? So how can we build better synthesis techniques to take us from high-level specifications down to essentially the assembly language of quantum physics? And it's a hard problem, but again, we're seeing interesting developments. There was a paper at Popple 2 years ago on using program synthesis to go from such high-level specifications down to circuits. But the problem is still open, and I think we have a great opportunity in the PL community to build these high-level composable abstractions along with compilers to help bringing them down to circuits. And I think we can save a lot of years of research on the parts of natural scientists as well as algorithm designers. For example, in quantum computing, you always hear the refrain that we don't have enough algorithms. And it makes sense that we don't have enough algorithms because, one, it's hard to think. The intuition is very different when you're coming up with quantum algorithms compared to traditional algorithms. Two, we don't have quantum computers to tinker with. Okay, the ones we have are very small and very hard to get access to. So by building high-level abstractions, I think it will allow us to automatically discover new quantum algorithms. Okay? We can simply start building program synthesis loops. So program synthesis loop will look like this. Propose an algorithm. Maybe you can use an LLM. Maybe you can just enumerate, whatever you like. Verify that it's actually doing what you intended to do and that it's giving you the speed up that you want, an exponential speed up on that problem, and rinse and repeat. So this may have looked outlandish 2 years ago, but with the cost of verification dropping close to zero, it may actually be feasible in the next year or two, and we may use this loop to actually discover new algorithms. So I think this is a grand challenge that we can potentially participate in, maybe even lead. So this was the story about taking a specification and turning it into a computational artifact. And now we move to chapter 2, which is metamorphosis. So now the circuit has to transform in a number of ways. And the key way is optimization. Okay? And this is what I'm going to cover in this talk. So optimization is exactly what you may expect. You're going to take a big circuit. You want to turn it into a small circuit. More or less, that's what we always do. And even at this PLDI, we had a couple of papers yesterday on circuit optimization, because it's a critical problem. If you have an optimizer, you may be able to run a circuit today. Without it, you won't be able to run it until, say, 5 years from now. So this is a tangible way of advancing the boundaries of quantum computing. hydration break. Play the ads. All right. So what's the trouble with optimization? One, of course, compilers are hard to get right. Quantum compilers are also hard to get right. There are even studies already, this paper from OOPSLA 2022, on the bugs that you find in quantum compilers, including the optimization passes that you have in them. And this is expected because they're hairy, you have complex numbers, and so on and so forth. You'll make mistakes. Second is that there is no instruction set architecture. We have many, many instruction sets. At the beginning of this talk, I showed you 4 instructions. This is a universal gate set in the sense that you can use it to implement any quantum mechanical phenomena. But if you look at a computer like from IBM, they've cycled through many different instruction sets. They're all universal instruction sets, but they keep changing them. And the reason they keep changing them is because the underlying hardware is changing fast. Okay? And some things are easier to implement than others, so physicists keep changing things. And if you look past IBM, there are dozens of companies out there that have raised billions of dollars, and they're building computers using vastly different technologies. Okay? And each of them has a different computational model, has a different instruction set, and they require different kinds of optimizers. So when my student, Amanda Shu, saw all of this, she was like, let's stop the madness. Let's just build a synthesizer for optimizers. Let's just generate these optimizers automatically. So the idea is very simple. We're going to take an instruction set, like the one I showed you at the beginning of this talk. We're going to give it to an optimizer synthesizer, and it will give us an optimizer. And hopefully this optimizer is verified in the sense that its transformations are semantics preserving. So let's see how to do that. First of all, what does an optimizer look like? Under the hood, an optimizer is really just a bunch of rewrite rules. At least most optimizers look like this, just like a peephole optimizer. So here's an example rewrite rule. If you see 2 Hadamards in a row, they can cancel out. If you see C0 and 2 X's, then one of the X's disappears. But we also have symbolic rewrite rules, things that look like this, for example. If you have a rotation by angle θ1 and then θ2, you can sum them up and have a single rotation of θ1 plus θ2. Okay? So you can think of this as a symbolic rewrite rule in the sense that it's an infinite family of rewrite rules for every possible instantiation of the angle. And things can get even hairier in the sense that you can combine 2 rotations, like as you see here, as long as a random subcircuit between them satisfies certain conditions. So this is, again, an infinite family of rewrite rules, depending on the circuit that sits between them. So there's a universal quantifier, if you will, on a set S. So what we want to do is we want to synthesize rules that look like this for a given instruction set. So how do we do that? Let's think of the most naive way to do it. Okay. Let's start with an empty set of rules. Let's enumerate a whole lot of circuits, potentially with unknowns in them. Let's say we enumerate billions of circuits up to some depth and width. Okay. And then we're going to look at each pair of circuits in this set. We're going to verify that this pair is equivalent. And if they are equivalent, then we have a potential rewrite rule C1 to C2 or C2 to C1 if you want. Yeah. This is, of course, a bad idea. Do not try this at home. There is a quadratic explosion, as you can see. And usually we're not scared of the quadratic in programming languages. But when we're dealing with billions of circuits, this number is just going to blow up. And it's going to be like 10 to the 18 or something like that. So what we ended up figuring out is that you can actually take this quadratic explosion and turn it into a linear pass, or an effectively linear pass. So how do we do that? So the first insight is that we can represent the semantics of quantum circuits as polynomials. Okay? Good old polynomials, high school polynomials. Okay? So we can take 2 circuits, translate them into polynomials, and now the equivalence checking problem is essentially checking the equivalence of those 2 polynomials. So let me tell you how we can do that. So this is an operation that I showed you earlier. It looked like this. We took the amplitudes and multiplied them by a number, and we got a new state. So imagine that this transformation is implemented by some circuit, by some program. Okay. This transformation is effectively, the way I'm representing it here, is effectively Feynman's path integral formulation of quantum mechanics. Feynman's path integral formulation says that a particle takes many paths in space to arrive at a destination. Okay. And the red arrows that you see on the left are the paths that a particle takes in space. Okay. So you can take those paths, or this transition relation, if you will, and literally enumerate them. There's exponentially many, but we're dealing with small circuits, so that's OK. We can afford the exponential explosion. And in general, because we're dealing with circuits with unknowns and symbolic variables, these numbers are actually expressions over complex valued variables. Okay. And I can enumerate all possible paths, 0 to 1, 1 to 0, and so on, and come up with their expressions. And then I can turn each of these paths into a monomial. Okay. So I can say A multiplied by some gadget V00, denoting the path 0, 0. Okay. So you can think of this V00 just as a toggle, on or off. Give me A or don't give me A. And I can do that for every path in this set. And then I'm going to add them all up. And this polynomial that arises is effectively a lookup table. I can set the variables V00 and V01, and et cetera, appropriately to extract the value of A, or extract the value B, or extract the value C, and on and on. So this is a general technique for representing the semantics of symbolic circuits, or as a class of symbolic circuits, as polynomials over complex numbers. So now that everything is a polynomial, checking equivalence becomes actually quite interesting and quite easy. So we can take two circuits that we want to check their equivalence, turn them into polynomials, and next what we will do is apply a randomized algorithm. So we're going to evaluate both polynomials on a random sample A. So we just assign each variable a random value in this polynomial. And if these two polynomials return the same answer, evaluate to the same number, then we say that they're equivalent. Otherwise, we say they're not equivalent. So this algorithm follows from the Schwartz-Zippel lemma, and it's a standard randomized algorithm. So now if the two circuits are equivalent, then the algorithm will return true, because the polynomials will evaluate to the same answer, regardless of the input. But if the two circuits are not equivalent, then the algorithm may make a mistake and tell us that the circuits are actually equivalent. But this probability of a mistake is very, very minuscule, and it's proportional to the inverse of the size of the domain that we're sampling from. So if we're sampling from 128-bit integers, we're talking about a probability of 2 to the negative 128. So it's effectively 0. So this randomized algorithm, if you look at a standard textbook, in the field, you won't find it in the chapters of the book. You'll find it in the introduction. So it's kind of like a poster child of randomized algorithms. And it turns out that we can take this algorithm and extend it to an arbitrary number of circuits. Specifically, what we want to do is we want to take a bunch of circuits, let's say billions of them, and put them into equivalence classes, such that if two circuits land in the same equivalence class, they can construct a rewrite rule. So that's what we want to do. How do we do that? We developed a data structure called the polynomial identity filter that simply works as follows. We take each circuit, turn it into a polynomial, evaluate all of them on the same random value A that we sample from a big domain, and then if two polynomials evaluate to the same answer, let's say those two evaluate to 0.5, then they will land in the same bucket, and we can treat them as a potential candidate rewrite rule. So this is all you need to do. It's a linear pass. There are adversarial examples where you get a quadratic explosion, but in practice you don't see that because the equivalent circuits are relatively sparse. So of course you have a probability of error. You can get a wrong rule, but the probability is still so small. You still have a birthday paradox type of situation. So you see an n squared over there. And this is what I warned you about at the beginning. But worry not, because the denominator is exponentially sized. So it's going to swallow this quadratic explosion, and it's going to disappear effectively. So in practice, we're talking about error probabilities at the order of 10 to the negative 20, something negligible. Okay. So this was kind of a fun discovery, like a multi-way arbitrage opportunity where we got ideas from quantum mechanics and path integrals and path sums and randomized algorithms, and we applied them to develop optimizing compilers. It was kind of an unexpected turn of events, but it actually surprisingly works. So now you do this, and you get a bunch of rules, maybe thousands of rules, and you have to apply them in a way. You can apply them in, of course, any order that you like to a circuit. And we've evaluated a lot of ideas. Yesterday, there was a paper on using equality saturation. So there's many ways to do that, and I'm not going to talk about the details of that. Okay. So how good are these optimizers that we can synthesize? So I'll give you an example on a real-world quantum computer specification. So we took one of the IBM gate sets, and in about a minute, we could synthesize a set of rewrite rules for it. We ran our optimizer using these rewrite rules on a large set of benchmarks, about 250 circuit, diverse set over many different kinds of applications. And we managed to outperform all the optimizers that we can find from industry, from the academic literature, from the national labs as well. So for example, compared to Qiskit, which is the standard toolkit from IBM itself, we can outperform it on 95% of the benchmarks, and with a significant margin per circuit. So it's a significant additional reduction. So I think this is kind of a nice example of the power of program synthesis and verification. If you scaffold the problem correctly, you can construct systems that potentially outperform handcrafted ones and ones that have been honed over years, which is pretty nice. So if you're interested in the intricate details of how these rules apply and how we synthesize them, the recent ASP+ paper and the PLDI 2023 paper are where you should go and look. And I also encourage you to look at the papers from yesterday in the quantum session, because they're also very relevant in this space if you're interested in optimization. So there's still a lot of open problems in the optimization space. One of them is the fact that most optimizers are completely monolithic. They just take a complete big circuit and just optimize it. But these circuits are coming from individual components. There's adders and multipliers and quantum Fourier transform and so on. So the modularity is completely unheard of in quantum computing in some sense. So we really need intermediate representations and modular optimization techniques. Second, the current state of optimization is designed for kind of the first iteration of experimental quantum computers, very, very small. So they don't scale to millions of operations or billions of operations, which is what is expected of future algorithms like Shor's algorithm and chemistry simulation. So they simply don't scale. So there's lots of room for development of interesting linear time algorithms for scaling to very large circuits. And I think ideas from program analysis and compiler optimization can help a lot here. And finally, circuit optimization is typically working at the logical level. So they're completely unaware of the underlying device which we're targeting. And this brings me to the final chapter, collapse. So now we have an optimized circuit, and we want to run it on a quantum computer. This is known as the mapping and routing problem. You have heard of routing from FPGA routing and VLSI routing. Ultimately, it's a hard problem. So let me illustrate with an example. This is a superconducting quantum computer. It typically looks like this. The circles are the qubits. So this computer has 9 qubits. They're laid out in this grid. And these are connections between the qubits. And these connections dictate on which qubits you can perform binary operations. So between these 2 qubits, I can perform a binary operation, like a CNOT, because they're connected. But between these 2, I cannot, because they're not connected. There's no direct path between them, or direct edge between them, not a path. So this makes the job of the compiler complicated. And let me explain with a concrete example. So let's look at a smaller device with only 4 qubits. Okay. Here on the left, we have a circuit with 2 gates and 4 qubits. These 2 gates are completely parallel. Gate 0 is operating on Q0 and Q1, and gate 1 is operating on Q2 and Q3. Okay. So ideally, you should be able to run them in parallel. So the first thing that a compiler does is it maps the qubits in your circuit onto the device in the same way that you may do, say, register allocation. Okay. So let's say we put Q0 here, 1 here, 2 here, and 3 there. This is a pretty bad mapping because the red qubits are not connected and the gray qubits are not connected. So to recover from this bad mapping, what the compiler needs to do is to insert a swap operation. So the swap operation swaps 3 and 0, and now the gray qubits are next to each other, the red qubits are next to each other, and we can run the 2 gates in parallel. So the job of the compiler, therefore, is to find a mapping that minimizes the amount of swaps that it needs to insert throughout a very large circuit. So this is the compilation problem here. So these are superconducting computers, and they're very well studied because they were the first ones to come online about 10 years ago. In the recent years, people have started taking this idea and adding error correction. The reason is quantum computers are very susceptible to noise. So you can get bit flips and amplitude flips all the time. Okay? It's at a very high rate. So you need to do error correction. And once you do error correction, the architecture changes significantly. So now your computer looks like this. What does this mean? Still a grid. These are your data qubits. This is where you place your circuit qubits. And these are some temporary registers, if you will. Okay? And each of these qubits under the hood is really a sea of qubits pretending to be 1 for fault tolerance. In case one of them flips, we can detect that. Okay? But we don't think of them that way when we think of the compilation problem typically. Okay? So now the first thing that the compiler does is it takes your circuit qubits and puts them onto the device. Let's say we put them this way. So in order to perform an operation like G0 between the red qubits, you have to find a path between them through the temporary registers. Okay? So this is a process called lattice surgery. And the path has to have a certain shape. So it has to start at the bottom of a qubit and arrive at the side of a qubit because of coding theory intricacies. So this is great, but now we've blocked any possible path between 2 and 3. Okay? So we effectively serialized this parallel circuit that we see on the left for no reason. Okay? So again, a bad mapping that we started with. So the job of the compiler in this space is to find the set of snaking paths through the temporary registers that do not overlap and to maximize those in order to maximize parallelism and minimize the amount of execution time and potentially error as well. Now, things get very interesting in other kinds of quantum computers, in neutral atom quantum computers to be particular. These made a big splash a few years ago and are now a big contender in this space. So in these computers, every qubit is represented by an atom held in space with lasers. And you can literally move these atoms around, okay, and then perform binary operations between qubits and then put them back in place. Okay? So it's very sci-fi, but it's a very different computational model. So now the compiler has more degrees of freedom. It can literally move things around in space. And there's, of course, error probabilities involved and stuff like that. So when superconducting computers arrived on the scene about 10 years ago, IBM put them online so anyone can use them, researchers started studying the compilation problem for such computers and started writing a lot of papers on this kind of stuff. And then a few years ago, error correction became a physical possibility. There are experiments shown that you can actually do that. And people started studying the compilation problem for error correcting computers. And then again, neutral atom computers made a big splash and showed that they can actually work and scale. And people started writing papers about how to compile for such architectures. Okay? And this is a very, very tiny slice of the sea of papers on ion trap computers and photonic computers and on and on and on. And look, I love writing papers. It's a lot of fun. Sometimes I do it, and sometimes my students do it. But you know what's more fun than writing papers? Not writing papers. It also saves the environment. So this has been the motivation of my student, Abtin Molavi. So Abtin looked at all kinds of papers out there. He talked to physicists across many fields and computer architects to understand what is going on. Okay? And what he discovered is that there's actually a very simple abstraction with which you can describe all of these problems. Okay? So with this abstraction, we can automatically generate compilers or mapping and routing specifically for different devices, including existing ones and future ones. So the idea becomes a compiler generation problem in the same way that we have parser generators and lexer generators and so on and so forth. So we came up with a little language called Amaro for abstract mapping and routing. There's also a Rust library, so you can write directly in Rust. This is kind of a language of constraints that describes the processor. Can qubits move around in space? How long does it take? So time can be encoded, error probabilities if something can go wrong, et cetera, et cetera. Given this information, we have a compiler generator that generates a compiler for that device. So how does it work? What is this abstraction? So the key abstraction is that we think of a processor as a big weighted state machine. So QPU here stands for a quantum processing unit, analogous to a CPU. So what is the state machine? What is the state in this state machine? If you like freeze frame and look at a processor at any point in time, the state of the processor is where the qubits live on the processor, where they're mapped, and which gates are executing. Okay? In the same way that if I look at my processor right now, I can see what's happening in the registers and which instructions are pipelined. And the transitions is movements between states. So things like data can move, different instructions can execute, and so on. And these transitions are weighted. There's a cost associated to them. It's an abstract cost. Different machines have different kind of cost models, whether it's a timing model or an error model, et cetera. You can encode all of this in this state machine. So to give you an example using the superconducting kind of computers, this is a state of the machine at this point in time. The data is mapped as follows: 0 on top, 1 at the bottom, et cetera, et cetera. And nothing is executing in this state. There are no operations being executed on these qubits. Now we can perform a swap 0 and 3, and pay some 1 unit cost. Here I just call it $1, but it could be really any kind of cost. And then in this next state, I can perform these operations G1 and G0, which is what we did in the previous slide. So this is a transition in this machine, and on and on and on. Of course, in practice, we don't write this state machine explicitly. We want to represent it implicitly. So this is now just an abstract model for us to think about the problem. So now the job of the compiler, abstractly speaking, is the following. Given a circuit, like the one on the left, and a state machine for the device at hand, you want to find a trace through the machine that is of minimum cost and executes all the instructions in this circuit. Okay? Of course, getting the minimal trace is usually very hard, so you try to optimize and get the best effort trace, typically. Okay? So for this circuit on the left, this is one possible trace. It's a suboptimal trace because I paid for a swap and I really didn't have to pay for the swap. But this is a trace that realizes all the instructions in this circuit nonetheless. So this abstraction works out for really any kind of processor that we could get our hands on in the literature. So to describe these state machines, we built a little DSL. You don't have to understand the stuff that you're going to see on this slide. It's really just 2 blobs of code describing this state machine. So the first blob, and this is using the superconducting example. The first blob here tells us which states are feasible. Like, in other words, which gates can you execute where. Okay, so you can think of it as defining the state space. And then the second blob tells us how do we transition between states. In this specific example, we can transition using swaps, and we pay some cost associated with this swap, $1 per swap. But you could also use probability costs if you want to simulate a failure probability of this operation, for example. So this is all you need, about 10 lines of code, and you can represent a problem that people have studied in dozens of papers. So semantically speaking, this Amaro program represents a state machine. And if you're given a circuit that you want to run on this device, you have a subset of the traces of this machine that can realize this circuit. And now the job of the compiler is to find the smallest possible trace, or as small as possible. Okay? So now the compiler generator is really just a solver that finds traces in a state machine, in the same way that a parser generator is just a solver that checks if a word is in the language. Okay. So how do we find such an optimal trace? Over the past few years, we've explored a number of algorithms, including optimal algorithms using SAT and max-SAT solvers, as well as stochastic algorithms that are approximate using program analysis type of techniques. And finally, it culminated in a POPL paper back in January, where we have this Amaro language, as well as a generic solver that can solve any problem in this language. I'm not going to go through the details, but it's a stochastic solver under the hood. So we took Amaro and we encoded in it all kinds of computers that are out there, including ion trap computers, neutral atom computers where things can move around, various formulations of superconducting computers as well, okay? With a few lines of code each, 10 to 100 lines of code, roughly speaking, depending on the complexity of the device. We also encoded fault-tolerant quantum computers using surface code and various computational models on top of that as well. And what's interesting is that after we put up the paper online and the code online, Google, with the help of Amanda, used it to generate a compiler for their early fault-tolerant architecture. So to evaluate their architecture, they needed a compiler, and they generated it automatically using Amaro. So that was an exciting validation of the work that we were doing, because we didn't know what Google was doing. And Google is one of the largest research organizations in the quantum space. What was astonishing to us is that across all of these case studies, the performance of our generated compilers either was closely matching the handcrafted ones and sometimes actually exceeded them. So I'll give you an example. This is a paper from Fred Chong's group at the University of Chicago. It's an architecture paper. It presents an architecture for neutral atom quantum computers with error correction on top. It's a pretty nice paper. And to evaluate this architecture, they built a compiler. Okay? So the reason people build compilers is just to realize how much resources are needed, how much time is needed to execute a circuit, how many clock cycles, et cetera. And then we took their approach, encoded it in Amaro, and our generated compiler was actually better than their compiler on the majority of the benchmarks. So in some sense, we demonstrated that their architecture is better than they thought it was, which is pretty cool. And this got us thinking, maybe we can automatically discover architectures. Okay? We can build a program synthesis loop to discover new architectures. So you can generate an architecture, propose one. Perhaps you can enumerate or maybe use an LLM to propose one. You can generate a compiler using our approach and evaluate that architecture using that compiler on a set of applications that you're interested in, and rinse and repeat. Okay? So this is, again, I think at this point in time, it's a feasible reality. We can actually do such things and discover kind of interesting and unintuitive architectures that probably a human would not have thought of before. Another interesting open problem, in my view, is verified compilation at this very low physical level, specifically for fault-tolerant computers. In order to run things like Shor's algorithm and do chemistry simulation, almost everyone agrees that we need fault-tolerant computers. And error correction causes a lot of complexity when it comes to compilation. So let me explain. This is a binary operation, a CNOT, a very, very primitive operation. You can't go like simpler than this. When I described how it runs on a fault-tolerant computer, I showed you this abstract picture. It's a nice, beautiful orange path going to 0. It's actually orange in the slides, by the way, so I'm not colorblind. So, yeah. But under the hood, remember that each of these qubits is really a sea of qubits under the hood, masquerading as one. So this single binary operation ends up being thousands of physical operations, right? Thousands. It's pretty crazy. So how can we prove that whatever we have on the left, this single lowly CNOT, is equivalent to these thousands of operations? Yeah? And even if we know that these protocols are correct, and a lot of people believe that they are correct, and they've simulated them and so on, having a verified scaffold allows us to aggressively optimize the underlying physical operations without fearing that we've lost correctness. So I think this is an exciting avenue for PL research. And we're starting to look at stuff in this space. My student Stavan Jain started the quantum error correction in Lean project, and he's formalizing quantum error corrections from the ground up with the hope of building a fully verified compiler going from the left over here down to physical operations. So this is what I wanted to say today. Walk through conception, metamorphosis, and the final collapse of a quantum state. And I hope to have convinced you that the kinds of work that we're doing in programming languages can be greatly impactful to the development of quantum computing. So this is the Cool Quantum Compilers project. It's a joint project with computer architect, Professor Swamit Tanu. And it's completely funded by the National Science Foundation. So we thank them for their support. And I thank you for your time. That's it.
Hi, it's a very good talk. I'm
Thank
Ganesh Gopalakrishnan from University of Utah.
Yeah.
So there was a period in high-performance computing where bit flips are a problem, and they had designed many techniques for redundant computation and so on. So is it possible to replicate quantum circuits and vote or find the majority probability for a certain outcome? What are your thoughts on error correcting using redundancy?
Yeah, so there's a lot of work on error mitigation. Where you're just kind of maximizing the probability of success by, for example, repeating a computation or running different computations that are semantically correct, so kind of an ensemble-like approach. The understanding in the field is that it will not scale to the kinds of computations that we expect in the future with millions of operations. Eventually, the error probabilities catch up and overwhelm the problem. So everyone kind of moved to this more fault tolerance approach that is provably scalable in the sense you can add the number of qubits and reduce the probability exponentially.
Hi, yeah, thanks a lot for a very nice talk, especially for those of us who know nothing about quantum, right? So very helpful. But okay, so you mentioned the idea of having conditional rewrites. Right. In other words, having rules that you could apply that might depend on, I suppose, some invariant about the state that you need to know. And you talked about this technique of finding equivalent circuits, right, that you could use as rewrite rules. Is there a way to synthesize rules that are conditional rather than unconditional?
Yeah, so some of the rules I kind of abstracted things a little bit for the purpose of the talk, but some of the rules that we generate are conditional in the sense that they look at this inner state, inner subcircuit, and look at its semantics and abstract its semantics and say if it does X, Y, or Z, then you can apply the rule, otherwise you cannot. So they are conditional in that sense. They're doing a very local program analysis, if you will, as opposed to a global program analysis. With a global program analysis, you can do more aggressive rewriting, but at least for the purposes of this work, it was a local analysis.
Right.
Yeah.
Okay, thanks.
Yeah.
Hi, really nice talk.
Thank you.
This might be related to the previous question, but I think you acknowledged in a previous slide that the swap that you inserted was technically suboptimal. You could have just like remapped the qubits from that start in that particular circuit. Do you have anything that like addresses that?
Yeah, so under the hood, the solver that's trying to do the compilation usually goes through multiple maps. So if you're doing, for example, if you're using an optimal approach using SAT solvers, in principle, the SAT solver is searching the entire space of all possible combinations of maps. If you're using a stochastic solver, it's going to randomly generate a bunch of maps and takes the best.
When you say maps, do you mean like initial maps?
Initial maps, that's
Okay,
right. Yeah,
okay.
yeah. So does that answer your question?
Yes.
Cool.
Yeah. Thank you.
Yeah.
Hi, great talk.
Thank you.
You said relatively at the beginning that when you do equivalence for physical components, it's not exactly equivalence like we think about it. It's a more fuzzy or physical or whatever notion.
That's
I was
right.
wondering if you could say a bit more about that.
Yeah, so the issue, I guess maybe we can walk to the beginning. I can't find a slide at this point, but I'm going to guess. Maybe it's slide 18. No. Let's see. Slide 22, so not too far. Yeah, so the issue is that you take this formula, e to the I ht, and then you approximate it, and that's the only way that you can generate a circuit. So that's where the approximation arises. And therefore, what I was saying is that ideally you want the compiler to be correct up to some epsilon bound. So the target program is equivalent to the source program with some bound on the error and the difference. Does that make sense?
Yeah, is it just a numeric bound, or is it some physical properties?
It's a numeric bound. This problem also arises in the compilers that we also built. So some of the rewrite rules that we synthesize or we construct, particularly in the ASPLOS paper, if you're interested, are approximate as well. So there's a degree of approximation there. But even at the level of a physical computer, because some of these operations have angles in them, you can never get a pi. You can get very close to a pi, but so there's there's some tolerance there. Yeah.
Thank you.
Cool.
So on the topic of architecture discovery,
Yeah.
I don't know whether, is there kind of work on thinking about what's a programmable quantum architecture? Because in a sense, like sort of arranging circuits is how we did computers in the 30s and 40s,
right,
and
yeah.
then the sort of programmable architectures like von Neumann kind of came about. Is there an analog for the quantum world yet?
Yeah, there is an analog. I think the interesting things is that because of the underlying differences in hardware, some hardwares are amenable to kind of a von Neumann style. For example, in neutral atom machines, where you can move things around, people are proposing von Neumann style architectures, but with superconducting machines, that's kind of feels impossible at this point in time. So there's all kinds of proposed architectures there, including the von Neumann ones.
Yeah. Yeah, so something that's like programmable. So
that's right. You could say they're programmable. Yeah.
Great. Thank you.
Yeah.
So for your rewriting rules, so you have thousands or like maybe even like 100,000.
That's right.
So it's significantly different from what classical has, right? So do you think it is still useful, and how much time do you need to discover, and you need to store them, and when you try to do the matching, pattern matching, so it also costs some time, right?
Yeah. So let's walk through these problems one at a time. So generating them is very simple. So the number I showed, which is 1 minute, that's just generating a compiler for an IBM style machine. So just takes a minute.
No, I was just asking for rewriting
Yeah,
rules.
we'll get there. Yeah, so that's generating the rewrite rules for an IBM machine. And then applying the rules, typically it's a stochastic algorithm, a super optimization style algorithm. So typically, at least in the experiments that we've run and others have run in the field, they give it an hour timeout. And the idea there is that these computations are going to run on an expensive device that you might as well spend a lot of classical compute before you send it to the device, in the same way that, say, a large training run takes a lot of money in machine learning, and you'd rather optimize ahead of time before you hit the GPUs. But there are recent discoveries on minimizing the numbers of those rules, so you can go from thousands to like 100 rules by removing redundancy as well. We weren't very aggressive when we did this work, but there are recent results that I've seen doing that. And in terms of applying the rules, ultimately it's a pattern matching problem, so it can get hairy and you're over graphs. Quantinuum was inspired by our work and work from Jens and others, and built a very fast pattern matching library in Rust. So and there's other opportunities for parallelism that we've been exploring as well. Yeah.
Okay. Another question is about this is approximate equivalence, right? Mm-hmm. So when you do compiler, you want to do, the error would accumulate. How do you deal with that?
Yeah, I think if you're building a large-scale compiler and you're proving that it's correct, then you might prove a theorem per pass of the compiler and show that this accumulates an epsilon, this accumulates epsilon, and then the final is 2 epsilon, for example. So I imagine people having compositional compilers that you can reason about like that. Yeah.
Thank you.
Hi, Elon Buzzetti, University of Texas at Dallas, aka the MIT of the South. This is on the topic of searching for circuit optimizations.
Yeah.
In that you said that these polynomials are exponential in the size of the qubits.
Yeah, that's right.
Meaning that testing them for computational equivalence is exponential in the size of the input. and that's that computational feasibility rate of growth. And then later you mentioned that the error rate of these equivalence checks is also inversely proportional in the size of the domain, which is exponential in the size of the qubits.
Yeah.
Given that the error rate and the computational complexity of checking have the same asymptotic growth rate, I was wondering how does that same growth rate affect the practicality of this in terms of the size of the circuits for which we can search for optimizations?
Yeah, it's a good question. So the two growth rates are orthogonal to each other. So the growth rate in terms of the size of the polynomial is relatively bounded because the rewrite rules are small. I mean, these are peephole optimizations. You're not looking for very large patterns. In fact, even if you had the ability to look for very large patterns, it's a bad idea because these patterns will be too overfitted that you will never find them in real circuits. So you want small circuits with like 2 to 3 qubits or 2 to 4 qubits, something like that. So you can absorb that exponential explosion very easily. The error rate drops exponentially. So we're talking, and it's in terms of the number of rules that you enumerate, number of circuits that you enumerate, and therefore it's usually very small. Yeah.
Thank you.
Yeah.
Hi. I'm Stephen Holton from Northeastern University. This was a great talk. Thanks a lot. So my question is about hardware abstraction boundaries, right?
Yeah.
So I think a huge part of what made optimizing compilers work so well is that we kind of stabilized the cost model for the underlying hardware.
Yeah.
And so we had a good understanding of fewer instructions equals better and stuff like that, right? But it feels like in quantum, especially because of error correction and underlying physics, those abstraction boundaries feel very unstable and very leaky. And I'm just kind of curious, do you see that stabilizing or becoming more difficult over time as the hardware becomes maybe more specialized to specific problems or so on? I'm just curious which direction you see that going and if optimizations are stable or not, or if they're constantly changing.
Yeah, that's a great question. So in my view, I don't think it will stabilize, and I think that is true for two reasons. Reason number one is just because there are so many different hardware modalities out there, and right now they're moving in lockstep, right? Mm-hmm. So they're just, all of them are progressing, and they have vastly different constraints. So in addition, even the underlying theory, like the kinds of quantum error correction that people were talking about 2 years ago, are vastly different than today. So the underlying protocols are changing. Now, you could imagine one winner emerges, and that's it. But we're also at a time where you can do architecture discovery really easily. And these architectures, at least the way typically described, they're not baked on a chip. They're roughly a kind of a more software level architecture. So they're very malleable. And as a result, you could be like searching all the time for better architectures and generating new compilers. So we may be moving to that state. Yeah.
Interesting. Thanks.
Hey, Adam Japala from MIT. I'm speaking as one of the many people in the audience who probably dramatically upgraded their understanding of quantum compilation in the course of this talk.
Cool.
So thank you. This is the first time I saw what seemed like an analogy with the way we're used to thinking about computer architecture and compilation for classical systems, where you can have a grid of relatively simple compute units arranged in space.
Yep.
And there are a lot of familiar techniques in that world to try to maximize locality and minimize data movement. To what extent do the intuitions built from that kind of work port over to this world, and what are the big surprises where the problems are different versus, say, a compiler targeting a grid of small classical compute nodes?
Yeah, so I mean, I think ultimately there are very, very strong similarities because ultimately you're solving an NP-hard combinatorial problem. I think the big differences are in the perhaps fast-changing error model, going back to Stephen's question, and like in some cases you care about error probabilities and modeling these errors, but in classical computing typically you don't think of errors and error correction and accumulating errors over the course of a computation. So I think that's probably the big difference. And then just the huge diversity in the various constraints between, say, a neutral atom machine where atoms can move around and a different kind of machine where things are stuck in space. So I think that's I guess what motivated us to build these abstractions, and we couldn't like use existing tools. Like we had a lot of ideas. Oh, can we just use constraint solver? Can we encode it this language or that language or Alloy or something like that? And we had to invent our own abstractions to do that. Yeah.
Thanks.
Yeah.
Hi, I'm Sorry. Hi, I'm Bhargav Kulkarni from the University of Utah. So I was looking at like all the programs that you showed that could be, ran on a quantum computer, and these just seem to be programs that are currently prohibitively slow, like to run on your classical computers.
That's right.
But I was wondering if like quantum computing admits newer programming abstractions that we can't even think of right now, instead of just like trying to like run these programs that we know we can run, but it'll take like ages on computers we have right now.
Yeah, so I think the field has this constant debate where, on the one hand, there are algorithms where we know provably have an exponential speedup, or at least we believe the classical counterpart cannot, and people are fixated on those. But there are other people in the field who are using quantum computers in a more heuristic manner for solving optimization problems, even though there is no proof that says that here's an exponential speedup. So there are heuristic uses of quantum computers as well. And the past decade has had many algorithms in that space, QAOA and stuff like that you can look at. It seems to me right now, looking from the outside at that kind of sub-community, is that they have not had major successes in terms of applications. But you could imagine once these bigger computers start getting built that we can see a significant departure from the performance of classical computers for various optimization algorithms.
Thank you.
Yeah.
Here for any final questions offline, but let's thank Gauss again.
Thank you.